Yeah. You are starting to record.
Yep.
So it's a pleasure to have Professor Mucciolo here today to talk to us. Professor Mucciolo had his undergrad and master's at USP. His master's in 1988, and then he got his PhD from MIT in 1994. He came back to Brazil and was a professor at PUC, Rio de Janeiro, from 1996 to 2002. And since 2003, he's teaching at the University of Central Florida. He's a full professor there, and until May, he was the director of the physics department there. I understand that University of Central Florida is one of the largest universities in the U.S. Is that true? In number of students.
So it's the largest public university in the country right now.
It's
about 63,000 students.
Yeah, I was there once. It's a very big campus, a lot of students. A very nice place. Very hot, but very nice. And today, Professor Mucciolo is going to talk about extended temporal prediction of expectation values via machine learning. So, Eduardo, please, the microphone is yours.
Okay, well, thank you very much, George, for the introduction, and thank also to everybody there, Edson as well, for inviting me to talk today. So I'm very excited about this. I haven't given a talk like this ever because as the pandemic hit, I was still department chair, so I wasn't doing a lot of talks. So this is the first one I do in this format, so I'm very excited about it. I hope it goes well. I'm not so familiar with the system here, this RNP mconf, so I hope I can handle it reasonably well. I'm going to share my screen, which means that I'm not going to be able to see you guys on the video. So if you want to ask a question, if you want to interrupt me, you have to say something. Otherwise, I'm not going to know. I'm not going to see virtual hands, going up. So all right. So I'm going to start now sharing my screen. I hope it works. If it doesn't, let me know. So I'm going to click the buttons here, and you should start to see my screen.
Can it works. It's working. It's working.
Wonderful. Well, thank you. Thank you very much. All right, so today I'm going to talk to you about a piece of work that was developed in my group. It has to do with our curiosity of whether machine learning can actually make predictions for time evolution quantum antibody systems. Even though I'm the speaker today, I must say that this work was really almost entirely done by two of my group members. Justin Reyes was a graduate student in my group until last summer. Northern Hemisphere was July last year. So he graduated, he got his PhD, and now he's a postdoc at UCF. And he's the driving force behind this project. And he also worked with another student of mine, Deep Data, who's still finishing up his PhD. And he did a lot of the, as you're going to see later, some of the matrix product states calculations. So these two guys actually came up with the idea, developed the method, did the calculations, did interpretation, and I only came up at the very end to, when they were wrapping things up, and we've been constantly discussing. So, so let me give a quick overview what's going to be the talk like. It's not going to be a very long talk, and I'll explain to you later on why, because there's a lot of things going on still. But I'll start with a background and a motivation for why you're interested in this problem, and then I will jump into a topic or a concept that maybe not all of you know much about, which is the convolutional neural networks. So this is a machine learning technique, sort of a regression in a way to be able to make predictions based on some training. Then I'll talk about how we do the training set preparation. In our particular case, we use time evolving block decimation, which is a technique for doing both real and imaginary time evolutions, and we use matrix product states for that. Then I'll show you the results. I'm going to focus on one particular model, the Ising model with transverse field. We've done calculation for other models, but I'll tell you why I'm not presenting that today later on. And then I'll give you a brief overview of what we learned and what we think it should be the direction of this research. So, by the way, it's important to also tell you that we have kind of a previous version of this work. It's not exactly like what I'm going to present today. We put out in the archive earlier this year, but since then we realized that we could do things better. We're doing them better, so we're hoping to put a new version of the paper substantially better in about a month or so. We're just wrapping up some calculations. But if you want to, check things out, a lot of what I'm going to talk to you today is already there. So let me give you then some background and motivation. So, so the main focus now, or the main problem that we're trying to tackle, is time evolution of quantum many-body systems. And it turns out that this is a really, really hard problem. And the reason is like this, I mean, you learn in quantum mechanics that if you have an initial state, and the Schrodinger equation is linear, so you start with initial state, you apply the evolution operator, and you can get the state vector of the system in later time. And let's assume, for instance, that the system is time independent, the Hamiltonian is constant, and don't worry about the phone here, it rings all day. So we're going to build the evolution operator by just exponentiating the Hamiltonian, with the proper i's and t's and h bars. So once we apply the evolution operator into the initial state, right, we can do that. So one way to sort this out, how do you do the exponentiation of the operator, is to basically work in a basis where the operator is diagonal, right? For the Hamiltonian, that means the energy eigenbasis, right? So we can then rewrite this evolution operator in that basis, and all we have to do is to put these projectors, which are the eigenbasis projectors, and then the e to the minus IE and t, which is the phase factor associated to the energy eigenvalues. But to do that, you have to do an exact analyzation, right? You have to find all the eigenstates, all the eigenvalues, and this can be pretty hard. Why? Because if you have just give you an example, so if you have a system with n spins, right? Spins on half, so each spin has two possible states, so the overall number of states or configurations that you have to go through to diagonalize this Hamiltonian is 2 to the power n, and then because it's a diagonalization, usually it's a matrix operation, you gain another power 3. So the brute force naive way of getting this evolution operator written this way scales exponentially with the number of particles in your system. And that's not great, right? So if you go to 10 particles, maybe you can do it. 20, pretty hard. By the time you get to 30, 20, it's really, really difficult to do it. So, and this is well known, it's been around for a long time. There are alternatives to the exact normalization, right? In many ways, in some situations, depending on the system, you can explore symmetries. You can explore the fact that some systems are not super entangled. They don't need all the eigenbase states to give a good approximation to the evolution. So, and people have developed methods to do that. Sometimes they explore the fact that the interactions are very local in space, right? So they're compact, and you use that to create recursive methods. And one of them is this time-dependent density normalization group method that explores exactly this kind of locality of interactions. There's also another different version of the density matrix normalization group that is called the dynamical one, but again, explores some of the features of one-dimensional systems. And there's another technique that came about 10 years after DMRG, which is the time-evolved block decimation by Vidal, which is really, really good. And it has some resemblance to the DMRG approach. But it's really good if you use matrix product states to represent your states. So I'll talk a little bit about that a little more later on. And then there are methods that actually explore, again, the fact that the interactions are very local in space, and which results in sparse matrices. So there are good techniques, good approximations that you can use, you can employ, that explore this sparseness of the matrix, the Hamiltonian, for instance. And there are also methods related to polynomial expansions and so on. So I'm not going to talk about the details of these methods, but I just wanted to make you aware of that. But why then are we still interested in tackling this problem if there's all these methods out there? And the thing is that all these methods have something in common. Actually, have two things in common. One of them is that they focus on the state vector, right? They're really trying to find good approximations for the state vector as a function of time. And let's say if you want to calculate
Eduardo,
yes.
Sorry, your screen is not being shared anymore.
Oh, no?
Yeah, I don't know what happened. Your camera went off, and then a little bit after, the screen sharing finished.
Oh, I'm sorry about that. Let me
No,
go
no
back
problem.
then.
No, it was just the beginning of this slide. Not
Perfect.
this one, the following background. Okay.
This is good.
Yeah, this one went fine. Yep,
What
yep.
about this one?
Just the first sentence. Yeah,
Can you see it?
yeah.
Okay. Well, yeah, I'm sorry, but I don't know what happened. I didn't see any
Um,
warning of anything.
that's funny. Yeah.
I just realized for some reason you leave as a presenter, so I made you present again.
Okay.
Sorry about that. I'm not sure what happened.
No problem at all. So, but everybody can see now, right?
Yeah.
Okay, wonderful. So,
Yes.
all right, no problem. So let me carry on then. So again, so going back, so what is common among all these different techniques of tackling the problem that, without using exact generalization? So there are two things that they have in common. And I was saying that the first one is they focus on the state vector, right? So they're trying to find a good approximation for the state vector evolution as a function of time, and then use that to compute expectation values. And the other thing that is actually a little hard to understand, but it's actually pretty much ingrained in all these methods, is that they are actually exploring something that people who, especially people who quantum information, they know more about that. It's called the area law. It basically tells you that so long as you stay within a sector of the Hilbert space where the entanglement is not very large, meaning quantities that scale, that compute amount of entanglement like entropies and so on, as long as they don't scale with the volume of the Hilbert space or the whole number of particles, let's say this way, they're like what we call sub-volume or area-like, then the amount of entanglement is very small, which translates into essentially not needing very many, basis vectors to be able to represent your state vector very accurately. So all these methods, when they work really well, you have to be aware that probably is because they fall into a problem where they can compute things in a very small subspace of the Hilbert space. The problem is that if you want to go, full-fledged quantum many-body, and then go to very long times that, typically is going to start to involve lots of interactions. They're going to propagate. You're going to start to involve more and more states or eigenstates bases, in the energy basis. That's not going to work anymore. At some point, you're going to break down this volume law, and then all these methods will run into trouble. So you have these two things that are actually sort of, on one side is the focus on the state factor, which not necessarily is useful sometimes. Sometimes you're just interested in the expectation value, not the state factor. On the other side, you're kind of bounded by, the area law. So is there a way to move out of these constraints? And I just mentioned that often we want to have the expectation values, not necessarily just the state factor. So that's how we actually started this project. So we wanted to see if we can use machine learning as a smart way to be able to predict the evolution of expectation values without having to calculate the state vectors and without, not being clearly constrained by the area law. And you're going to see that, in some ways we succeeded, in others we did not. So, and just to tell you a little bit about, machine learning, what it means in this context. I mean, people have been using now machine learning quite a bit in physics, even in many-body quantum physics. And usually it's done in the form of a restricted Boltzmann machine, which is basically a way to, categorize, usually wave functions or probability amplitudes. But also they've used convolutional neural networks for that. But mostly the focus has been on probability amplitudes and, wave functions in general, and mostly in the ground state, right? Not so much for the excited states. And again, if you fix the accuracy, if you want to have a constant accuracy or a constant predictive power in your calculation, typically the computational cost can grow quite a bit, even sometimes exponentially, even with these methods. So what we're going to try to do now is to say, okay, let's see if we can do something different. So instead of focusing on amplitudes, probabilities, state vectors, we're going to try to focus directly on expectation values and see if we can get away with these constraints of the area law, and see if you can express accurately the evolution of the expectation value of some quantity for long times, because at long times is when the entanglement starts to kick in, and all the methods usually that I mentioned earlier run into trouble. And we're going to focus primarily on one-dimensional systems because they're fairly easy to compute, right? So they're paradigmatic in the sense that everybody knows a lot of results for them. We can always check things out. So before I do that, I'll talk about the convolutional neural network. I'm going to abbreviate by CNN, right? And so what is it? It's basically a way to approximate multidimensional nonlinear functions. So essentially, you have an input X, an output Y, and what you want to do is to compute, given a certain number of tests or samples, we're going to try to train this network, which is here represented by W. It's a collection of coefficients to give you some Y prime, which is hopefully a good approximation for the exact Y, right? So to be more specific here, so X is my input data, F is some kind of nonlinear activation function that turns on and off the neurons in the neural network. W is what I'm trying to find through some kind of optimization procedure by using the samples and the training to get the best possible W. It's like fitting a curve, if you wish. And W prime is my guessed output, which hopefully is a good approximation to the exact output, which I may not know every time, right? Interestingly, this method, this approach actually came about almost 40 years ago, and it came about in the context of computer vision. So a lot of people were interested in finding ways of training software so that they could recognize, for instance, zip codes. So people, when they send a letter, they write the zip code by hand, and not everybody has, nice zip, handwriting like Caio. Caio Levenkoff has a wonderful handwriting, and I can always understand it, but even my handwriting is terrible. I cannot even understand it myself. So imagine the poor machine that has to read, handwritten zip codes of millions of people, right? So they were trying to find at that time a software that could do that faster than humans. And so that's how this convolutional neural networks came about. It's just one application, right? There are many more. But so every time you go to computer vision and you look at the application of computer vision, most likely there is the CNN running behind it. So this scheme is like this, just to give you a very quick, I'm not an expert, so I'll give you a very kind of a bird's eye view of how the method works. So you have an input, could be like a picture, let's say, right? So you scan the picture, you create pixels, RGB, right? And then you send that to filters. The first one is a convolution filter. It basically, sweeps across the data and reorganize it. And the second one is pooling, basically takes chunks of data and do some kind of voting to get the best representative, or a number that best represents that particular set of data points and so on. And once you have that, you squash everything into a one-dimensional vector and you throw into this fully connected neural network, right? And of course, what you do then is that you compute some output with some weight function, and then if it's good, you keep it. If not, you move a little bit in your parameter space, and that's how you end up, finding an optimal matrix W, right? So that's how it works. So let me give a few more specific details about the CNN that we use in our work, right? So another diagram now. So I'm going to just, lump the convolution and the pooling all together into a single layer here. So what I'm going to do is provide some pairs of data points or vectors, X and Y, right? N is the index of the sample. So if I have 1,000 samples, N goes from 1 to 1,000. There is a kernel and a stride, which are parameters of the convolution. I don't need to talk too much about that, but you can ask me later. And then you have the neural network, you have the neurons. This ReLU is a kind of nonlinear activation function. It's basically like a diode curve, right? If you have a certain value, it does nothing. As soon as you pass a certain value, it jumps, right? So it's like a diode IV curve. So that's how this ReLU activation works. It's a nonlinear process. And then you can have many layers of this these neural networks. You can have 1, 2, 3, 4, and so on, and each one is going to have its own set of connectivity parameters, which are what these W's are, right? And at the end, you get some output, y prime. So now a couple of important things to mention is that for our work, we use just like a chi-square like cost function for optimization, just square distance. And we use a stochastic gradient descent and add optimization to walk through this parameter space based on this cost function. And what is our training sets, right? Because you have to provide some, what we call training sets, basically values of t and time and expectation values that they are correct to train your matrices W, so that then you can make predictions for times that are beyond that training time. So in our case, X is going to be just a bunch of time values, right? Equally spaced over a certain interval. And the Y is basically the expectation values of the quantity that are interested. So the idea here is that we're going to compute using any methodology, well, I'll tell you what's our favorite is, but you could in principle use any methodology to compute expectation values at short times, right? To get the machinery trained, and then use those parameters to make extrapolation towards longer times, right? That's the idea. So how do we prepare the training sets? So we need to generate these pairs of TK and OTK, always the observable that I'm interested at short times to make predictions at long times. So what we do is that we employ matrix product states and this block decimation algorithm, and I'll explain to you what that means. But let me put all this in the context of one-dimensional spin models with nearest neighbor interactions, because then things are a little easier to understand. So suppose I have a Hamiltonian, which again, it's one-dimensional. So I have sites, I is the site index, and I'm connecting site I with I plus 1, right? That's all I can do, right? I can have on-site, operators and potentials, fields, and whatever. But in terms of interactions, I only go as far as the next neighbor. So if that's true, I can use a trick. I can break down this Hamiltonian into two sets of commuting operators. And basically what I do is like this. So I have you can see here in the drawing with the black dots. So I have these black dots representing my sites where the spins are located. I'm gonna lump them into two groups, the red group and the green group. And the red group, you can see it's every odd and even site, right? But I don't have even odd, right? So in that way, I guarantee that every one of these pairs don't talk to each other. So all of them commute, right? Because my interactions are only nearest neighbor. And then I have a second set, which is the even odd set that goes across again the entire chain, where they also don't commute with each other. They commute with each other and they form a second group. Obviously, the red group and the green group don't commute with each other, but at least within those sets, they commute, which means that when I try to do the exponentiation of a matrix, I'm going to be able to break it down into like 2x2 matrices. Exponentiating in 2x2 matrix, everybody knows, right? You can use Pauli matrices for that, so it's a much easier task than exponentiating a 2 to the n matrix. But again, I still have these two components or two parts of my Hamiltonian, they don't commute. So how do I go about that? So in this case, we use something called the Suzuki-Trotter approximation. I guess, people in that group in Uberlândia probably know quite a bit about that because most likely they use that very often. So I'm going to do is that I'm going to break down my H again into this odd, even, and even odd. And then I'm going to approximate that exponential. So instead of writing the exponential to the sum is the product of the exponentials, I do something a little more subtle. I throw in, three factors, if you wish, with the proper phases. By the way, there's a delta over 2 missing here, the very last exponent. And by doing that, you can actually show that the mistake you make if tau is very small is second order. And you can actually have better, more accurate expressions that become more and more convoluted, that can go to third order, fourth order, and so on. For our purposes, we stop at the second order because it's good enough for what we're doing, right? So these are the two ingredients that we're going to use to compute, again, expectation values at short times. So again, I mentioned earlier that we're going to use this matrix product state representation. I could spend an hour explaining that, but let me see if I can do it in a few minutes or maybe a couple minutes. So the idea here is I'm going to rewrite my state vector. Let's say in the spin basis, I have n spin sites, right? Each one, let's say if it's spin 1/2, each one has two possible orientations, up and down, plus and minus 1. And I'm going to write the coefficients of that expression in terms of a trace of a product of matrices. And I have basically two matrices for every site, the +1 and the -1 matrix for site 1, and so on and so forth until we get site n. So this is what we call the matrix product state representation. This representation can be very efficient. And it happens to be efficient when the size of the matrices, let's say in this case, let's call it d by d, they don't grow exponentially with the system size. And in some conditions, they do. And sometimes we even want that to happen because it keeps accuracy, high accuracy. But in some cases, they don't. So, and we're going to explore that to some extent. So once we do that, once we have the MPS representation of the state, then we can rewrite using the Trotter-Suzuki approximation, can rewrite the evolution operator in terms of basically matrix multiplication, single value decompositions, and so on. And the beauty of that is that the computational cost of this scales with n, which is the number of spins, and the cube of d, because d is the matrix dimension where we're going to do like single value decomposition, which is a bit like diagonalization. So they go with the cube of the dimension of the matrix. So you can see now that so long d doesn't grow very much with n, this is, can be a pretty efficient way to do it. And we know that that's going to be the case when we have short time evolutions, that we don't really necessarily need to go to exponentially high d's. So yeah, and that's exactly, here in red is what I just mentioned. So as long as we are at short times and we break down the interval in enough of these Trotter-Suzuki slices and so on, we can get fairly accurate results for the short time evolution, right? And so once we have the MPS, the matrices, we can compute psi, then we can compute the expectation values and so on. And that's what we use for the training, right? Now, there are two things I want to mention. Obviously, if you only do that, you're only going to generate as many training sets or samples as in the number of points that you use for your short time interval. And sometimes that's not enough. So what we do is that we tweak some parameter in the Hamiltonian. So let's say if you have a magnetic field, we vary slightly the magnetic field. If you have some other interactions, we vary slightly that interaction so that we can get a larger set of samples to do the training, right? And the other thing that's actually very important, which is not in the archive paper, because that's something we learned very recently, it's also very useful to keep track of what we call two channels. So even if you're only interested in computing the expectation value of the z component of the spin, it's also very good to do the training in the x component, because these two non-commuting operators, when you train this, your neural network with two of them, and because they're non-commuting, you gain a lot more information without necessarily actually doing more calculations, right? You just multiply the number of calculations by 2, but the effect is tremendous in terms of the accuracy, right? So that's an important thing to mention. So let me again, I'm going to jump to results, and I hope you get excited. So we're going to use as a benchmark or as a reference the Ising model in the presence of a transverse field, one-dimensional system, zero temperature, right? So the Hamiltonian is very simple, right? So I have spin 1/2 dispersed on located on the chain, and they all have the same exchanging interaction J, and I put J positive, so we're looking at the ferromagnetic interaction here, and then I have a field in the x direction transverse to the Ising coupling, right? And again, the field is the same for all the sites. So we know this model is pretty simple. You can solve this exactly, at least the ground state, excited states, you can solve it. For small j, it's a paramagnet, right? The spins are going to be pointing in the x direction. For large j, larger than h, it's a ferromagnet, right? Every spin is aligned in the z direction. And when j is equal to h, you get a quantum critical point, where, by the way, you get the maximally entangled possible state for the system. And that's where we're going to be doing our calculations. So let me show you the results. So this is a plot of the expectation value of the z component the average Z component on the chain, right? As a function of time in units of J. And you can see that we started with initial state that was basically the eigenstate of the X operator in the plus direction, right? So it's basically, all the spins are pointing the positive X direction. And then, because it's we put J equals to H, this is not an eigenstate of the system. So it's going to find strange, it's going to oscillate and so on. And you can see that very clearly here. So it starts at 0 as Z, right? Because it's an equal superposition of plus and minus. Then it decays, and then it starts to oscillate and oscillate. And then you see some really cool oscillations that are pretty much periodic, right? Within the accuracy that we're able to tell, you can see they're periodic, right? There is some kind of preliminary oscillation here with no small amplitude, but later it becomes bigger and then it repeats and so on and so forth. And that's a kind of a beating. And the beating and the frequency of these peaks has to do with the number of sites. In this case, we did a very small system, 10 sites, just as a way to look at how things work. We can do bigger ones. We also swept the magnetic field around H equals 1. So this particular plot is for H equals 1/14 J's. And the time increments are, 0.5 of the unit 1, which is 1/J is the natural unit of time here. So you can see that. Question.
How long you can go in time?
We've been going to up to 20. And I'll tell you what limits it. It's basically accuracy. So we actually don't know. We can keep going, and I think the furthest we went is 20 units of J, 1/J. With accuracy that is reasonable, but I think we can push more. And I'm insisting my students, that they should not be lazy and they should keep pushing this to see how far things go. But yeah, that's how far we've done so far, right? With similar results, you can see that. Oh, by the way, I didn't explain what the data points are. So the crosses are for the CNN prediction, which, by the way, is done on this on the left-hand side of this green line. So this region here, I guess you can see my mouse, right? So the left-hand side region, on the left side of the green line is where we do the training, and the right-hand side is where we do the prediction, right? So we trained a little bit, and then we can predict all of that stuff, right? And the circles are basically the MPS calculation, because we also said, you know what, we can try to benchmark this. Obviously, with 10 spins, we could have done the exact diagonalization, but we also wanted to see how far the CNN deviates from the MPS along times, because the CNN was trained with MPS. And you can see that it, within this interval here, it deviates very little. Actually, I can tell you the deviation is about 10 to the minus 4, right? 8 10 to the minus 4, close to 10 to the minus 3. So it's pretty good. So basically, we trained with 50 time slices, and we made a prediction for another 200, right? That's how it went. Mm-hmm. Did I answer your question? Or maybe you're not there anymore.
Okay.
God, thank you. All right. So what else? Well, there are a couple interesting things here. So let's look at time scales, right? Because I want to try, the selling point of this is that I'm going to be able to do calculations at a longer time, accurate and efficiently. So let's look at how long it took to do these calculations, right? And obviously the 10 spins, you say, this is a joke, right? I can almost do it by hand. That's all right. But at least it gives us an idea of how things are going to scale. And I will show you data for larger systems. So the CNN training for this particular example that I just gave you took 200 seconds, right? Remember, the training has all these features that you collect you put the data into the neural networks, or do the optimization. Sometimes you run it several times. They're called epochs. I think we did 500 times and so on. So there is some time that takes to do that training. And then once you have the training set, you have all the parameters, then you have to do the prediction. Prediction is just a very straightforward calculation. It doesn't take much time. Now, in this case, because we use the MPS and TBD to do the training, I also have to compute the training time, which for this small system of 10 spins, it took just about 30 seconds. So you can see in this case, the training took almost a tenth of the time it took to do the training. I mean, the generation of the training sets took about 10 times less or 7 times less than the training itself. Now, you're going to say, but come on, 10 spins, how long does it take to do the exact normalization? Okay, it takes about a minute, right? So obviously, for such a small system, CNN is an overkill. It doesn't really bring you much good, right? Because you can do the exact normalization. Now, what happens when you start to crank up the system size, right? So let me show you some results, which actually we are adding more and more lines to this table as we speak. So, and by the way, this table was calculated for a different type of training, a training set where we did, we trained for a little longer than what I showed you, about 3 times longer, but also the prediction was for a longer time. So it's not exactly corresponding to the plot that I showed you, but it's very similar, right? And the error here was bounded to 10 to the minus 3. In other words, we did the training up to a point where we knew that the error would be 10 to the minus 3, right? Because obviously, if you don't train very much, you get something, but the error tends to be larger. So we use the error to bound, or as a bound for how much training we need to do to achieve our goal. So you can see here something interesting. The training time itself did not change much, right? Actually, if you look at here, I'm adding 2 spins every time I go from one row to the of the table to another one, and it's roughly linear. It's actually a little sublinear, right? But it really takes a lot of time is that generation of the training sets, right? Because remember I told you I use matrix product states. At some point, I have to allow the matrices in my matrix product state to start to grow to be able to accommodate all that growing entanglement. And when they start to grow, that's where time starts to really weigh in on this computation, right? So in this particular case, what I heard from my students that they allow the matrices to grow as far as they could, which in this one-dimensional systems tends to be 2 to the power n divided by 2. So the n is divided by 2, right? So so that's an exponential growth if you want to accommodate all the possible entanglements. So they just let it free, and that's how you see it here. So the training time, even at short times, is growing exponentially. It's still not terrible, right? But it's growing exponentially. Whereas the training itself is sublinear, which is kind of cool, right? So the training is not the main problem. And this graph more or less put all this into picture form. So you can see that when I compute the time to do the TBD, generation of training sets, I get an exponential, roughly, right? And when I plot in the time to do take the training set and the training time and then add the CNN, this is what I get. So by the way, the TBD here is the training plus the rest of the time, the entire evolution, whereas for the orange curve, I have only the MPS for the training period. So it's it's a smaller time, computational time. So you can see that eventually the CNN does win over the full-time TBD MPS computation of the evolution. So, and that's, it's written here what I just mentioned to you in words, spoken words. So now, we are very curious to see if we can actually reach much longer times than with this 1 over j. Because by the way, I didn't mention that, but most of the other methods that I mentioned, that I listed earlier, they do allow you to do this time evolution, but very rarely beyond 4 units of 1 over j or 5 or so. So usually they're stuck in that order 1 over j type of interval in time. In our case, we're already seeing that we can go to 10, 20 times that, right? But we haven't really pushed very far into larger system size to see how that scales. But we're getting there. So so that's the punchline. I think I've been talking for quite some time. Yeah, so 44 minutes. So I'm ready to wrap up. So, and I want to have time for questions because you guys may be curious about things that that I either spoke too fast or didn't talk at all. So so a few highlights, or a few thoughts. So what we learned there with this kind of exercise that we can use convolutional neural networks to predict long-time expectation values operators. It seems to work fairly well, at least for the systems that we looked at and for the range of sizes and times that we considered. It's interesting that when you fix the accuracy, the computational cost becomes attractive for large systems, so long as the training time remains low. And this could be challenging because it may be that at the end, the real bottleneck is still the generation of training sets and not so much the training itself, right? So we use the MPS and TBD method to do the short time training, but in principle, you could use any other technique. You could use time-dependent DMRG. You can use whatever you like, right? Sparse matrix exponentiation, kernel polynomial methods. You could use anything to do the training. We did MPS and TBD because in my group we have a lot of those codes already developed. On a more philosophical side, there's something that really bugs me about this, and this is where I keep asking my students to think about it, because ultimately what we're doing here is plotting a variable for a certain time interval over different conditions, right? Slightly changing, fields and boundary conditions, if you wish, or something like this. And then out of that, we're predicting what's going to happen to that variable at long times. And it's actually kind of mind-boggling that it works so well. So sometimes I don't know if this is, we found some really magic and really cool, or there's some triviality behind it. We don't know yet, right? But I just want to tell you that this is something that it's bugging me to some extent. And of course, there's a lot much more to be tested. So we are working on larger system size. We're running simulations now for 20. And the reason why we're doing that is because when we wrote the paper we put on the archive, we very quickly realized that we could have done better by changing the activation, neuron activation function, and also doing this 2-channel training. And so we're redoing the whole shebang of calculations, and including maybe adding some disorder to try to increase the number of training sets and so on. So and this is ongoing right now, and that's it. So anyway, so just to wrap up, of course, we did this training with machine learning for the time evolution. I always get this question but could you guess the evolution without actually doing this training, or is there another way to do it? I don't know, right? So I don't know if you can do self-generating machine learning for this particular problem. So maybe it's a question out there for somebody to tackle. And that's it. So I just want to finish acknowledging the funding that I received to do this work and other things as well from the International Science Foundation. It's a grant that just ended recently, and I was able to use that to support my 2 students. And thank you very much.
Thank you, Eduardo, for the nice talk. We have already a line of questions here.
Okay, let's see if I can see them.
Yeah, there was a question that was written here. Hi, everyone. I have a question. Is this delta a new computational parameter? I saw the question, but you were already further along, and I didn't want to.
Sure. Yeah. So let me jump there. Let's see if I can find. Oh, right here. Maybe it shows up. Yeah. So can you guys see my screen still?
Yeah.
Okay. Yeah. So basically, delta is I take my time interval. In this case, we call tau, right? And I slice it up into 100, 1,000, whatever number of slices you want. And delta is basically the width of that slice. So it's basically the time increment that I use to both do the sampling so that I can do the training, but also to do the evolution, right? We use the same time interval for both parts, the training part and the prediction part. Yeah, so it's just a fraction of the total time. So it is a parameter that you can, the smaller you use for delta, the more points you have, more calculations you have to do, but usually the better the accuracy. Yeah.
And we have Luis is in the line to ask a question.
Hi.
Okay. Yeah, Luis,
Hi, Eduardo. Thanks for the talk. Very, very interesting. And I'm also curious as you are regarding the story of, using the values of the observable as short time scales to predict the longer time. And I'm wondering if you have, say, a problem with different time scales, different characteristic time scales. And I can give an example here that we are all familiar. I mean, Edson, George, Caio, me, you, which is the Kondo problem, like the Anderson model, which has different energy scales and thereby different time scales. So if you have, say, if you want to reach the really long time scales regarding the inverse of the Kondo temperature, but you only calculate things on time scales that are short, will the physics be captured in that short time scales?
I mean,
to give
you nailed it. Something that bugs me because I agree with you that I would say no, you can't, right? Because you haven't been able to sample the dynamics of the system long enough to be able to see those things that happen at really, really long times, right? They're related to very, very small energy scales. But so it could be. We haven't got to a problem yet where we have a large separation of scales. So we've done a few other problems like the XXZ model where we do have the anisotropy, which kind of mimics to having 2 time scales. And for that one, we were able to do some pretty, get some pretty good results. The accuracy was 10 to the minus 2, and we stretched up to 20 units of time of J, sorry, and up to systems of size, I think 14. And we were able to do some really, really good predictions. So with 2 scales that are not too far apart, we seem to be able to handle it. And the training, by the way, was even at shorter time scales than for the Ising model. But if you have this very large separation of scales, I must say, we haven't done it, but I must say I would expect that somewhere things ought to be, break down. I mean, you cannot possibly have that much information in the short time, enough at least to do these long time predictions, unless maybe you train it with such a large number of samples that you're able to kind of extract some really, 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 weak correlations, even at short times that maybe will manifest themselves a long time. But that's actually a very good question. I don't have a definitive answer to that. My guess is that probably won't be able to do it, but one has to check. Yes.
I have a second very short question regarding, say, the hyperparameters in the CNN or things like that. That as far as I understand, sometimes the training is very dependent on those, like which kind of activation function or cost function you use. Do you see any dependence on that?
Yes, we do. So when my students were doing this calculation, I was not paying much attention to that. They were using linear activation, and I said, oh, cool results and so on. Then they wrote a paper sent to physical review, and the referee, the very first thing the referee mentioned, one of them, is said, you can't do this calculation with linear activation. And then I realized, oh, okay, I should have read this better. Yeah, I should have paid more attention. Obviously, no, you can't. So absolutely. And interestingly, the moment they used the nonlinear activation, things improved quite a bit, right? So they were able to lower the error by 1 order of magnitude. And also when they start to do this, double channel sampling, looking at 2 non-commuting variables at the same time to do the training, that was even another, order of magnitude gain, and they could stretch the predictions longer. So absolutely. So the training is very, very sensitive to what you put inside the model. In terms of, for instance, what does kernel equals 4 mean? It basically means the following. So when you're doing your training, you have to kind of break down your pairs of TK and OTK into groups. And the kernel here is basically how many of these points you group together, right? So when you pass through the convolution and the pooling. So you could use 5, you could use 3. We used 4. It seems to be pretty good. And so there are these things that you actually have to try out. And I think they will be very dependent on, particular model that you're looking at, the particular variable that you're looking at. So these things have to be kind of done in some semi-artistic or scientific way, right? You have to have some feeling for what are the best values, but absolutely. So there are some things that are very critical, like the activation and the number of training variables. Others maybe not as critical, like the kernel. I think if you go from 4 to 5, you're not going to gain much, but you have to try. Yeah, you have to check.
Okay, thanks.
Any more questions?
I have a question.
Yeah.
I have one.
Yeah, go ahead.
Nice talk. Nice talk, Mucciolo. Thank you very much.
Thank you.
It turns out, I think, right after you post your paper on archive, I sent you a message. And,
yeah, I remember.
But we have.
You told me it was too good to be true. Yeah.
Sorry about that. And it turns out that I think the plot you had in the paper you didn't show. So what? But here, the one that you showed here, the training window, and the rest of the time evolution, they are not quite the same, but you can see features on the right hand side of the green line and the window before. So in the other one, the other one I saw in the paper, they were completely different. Actually, yes. This has to do with Luis' question, and
yes.
And it was hard to believe that. Let's put it that way. How could the network capture some frequency or some information out of that part of the plot that had nothing to do with the rest? In principle, maybe there is something hidden there we could not see.
Yeah, it's a very good question, and actually, we're going to redo that paper entirely, because now I think that the actual features that we're seeing, that plot that we posted in the archive with the paper, that was probably an artifact of the poorly chosen activation function, right? So I don't believe in it anymore. And that's why we are redoing everything now, and everything is more consistent. Actually, I'm more on top of the students now, make sure that those things don't slip through. But this one is a good one. So this one actually Justin generated yesterday, and you can see very nicely the bidding showing up, right? And it's a recurring effect. And I think most of that is actually, it's hard for you to tell, but it's already sort of embedded into the short time domain, because once you start to train the system in your very slightly parameters, even though this time scale may not be fully developed, you already have tendencies there, right? So you don't have, let's say you don't have a full oscillation or 2 or 3 full oscillations developed within the training time, but you probed enough of that to start to be able to make some predictions. Of course, this is bound to fail eventually, right? So if you stretch this very far, you're not gonna be able to keep up, right? But at least, yeah, exactly. So at least in this case, we're able kind of to push by almost 1 order of magnitude using those features. Would we be able to push 2 orders of magnitude? Well, in a system where you have only maybe a few time scales, maybe, but in examples like the one that Luis was talking about, the Condo, where you have this very large separation of time scales, probably not, right? You're not going to be able to do it very accurately. Yeah, I agree. Yeah, but I just found it very interesting.
Also, if you have a more complicated model.
Yes, yeah.
Okay, go ahead.
And most likely, the bigger the system is, the more complicated it gets, right? To get to make those predictions. Yeah.
Yeah, but another feature that should come up if you have even that I think it will lie in the same class of problem we were talking about, because you have a more complex Hamiltonian, so then you have more frequencies if they are far apart from each other. So time scale will be different, so you need to go further in time to train your network. So, but the second, if George is not too angry with me, maybe a very technical question. And so this CNN, and typically you need to define how many hidden layers you need, right? So how
Yes.
sensitive is, maybe you have talked about that already.
Yeah, so what we find is that we don't need many. I mean, I think if you go back to this figure here, no, this one, yeah. So I think here, for instance, we have sort of like two, I mean, it's one layer of neurons, but we have two sets of Ws. That's pretty much what we do right now. We don't have many more than that. Could we have done more? Yes. We haven't really found it necessary yet. But that's another thing that we need to explore. So right now, the critical thing is really generating a good training set, and also looking at more than one variable. I suspect that you have models that have a multitude of non-commuting variables. You're probably going to have to follow up on more variables to do the training as well.
Oh, okay. By the way, the training set, the choice of training set is very smart. I like it very, very good. Thank you, Mucciolo.
No problem. You're welcome.
Any more questions? Anyone?
Yep.
Yeah, Xavier, go ahead.
About 10 years ago, I guess the people used linear prediction with DMRG, and we were able to get very nice results. I think it would be better than you found there. Did you compare these results?
We haven't. Yeah, so that's a good point. I think we need to do more homework. And even within this machine learning physics community, there are people now using different approach, but they're also trying to compute time dependence, and they're getting results which I think are comparable in some ways, but also better in others. For instance, there is a paper by a group in Dresden. They were able to do the 2D Ising model, two-dimensional Ising model, and they were able to push to systems that are 10 by 10, so 100 sites, using something similar to that, not exactly the way we do. They don't train with the expectation values. They still look at the wave functions to do the training and probabilities. But they were able to do 100 by 100 2D Ising model, which is pretty good, right? But they only can do up to time equals 4 over j, right? And so they were not able to push much further, but they can do a large system. So I suspect that I'm not claiming that we are state of the art for sure. I mean, I think we're probably far from that. But what I found very interesting is that this method is kind of low cost in a way, right? So long as you have some good way of, a reasonable way to generating this short time training sets, you can actually make predictions fairly well. And you can see that, even for a 10 by 10 spin, 14 spin system, we already beat MPS, right? At least for times up to 10, 20 units of 1 over j, which is, it's interesting, right? But, some people who are more specialized into doing one-dimensional time-dependent calculations may be able to push much further, and then we have to see if we can catch up. But we haven't been able to do that comparison very systematically. So I'll probably say that you're probably right. There are even better methods right now still, right? But this one is pretty interesting, I would say. So it might be, if you're going to do something quick, this might be a good way to do it.
Okay, thank you.
Any more questions? Anyone? I was going to ask about something that you mentioned. I was going to ask if there is any constraints that you have to do calculations with this method in one dimension, but you just mentioned that they did 10 by 10. So my question was going to be when we're gonna see this method, if you are able to tell that, or what is your feeling, this method making contributions to, for example, the Hubbard model in squared axis to make an impact on the high TC problem.
Well, I don't know. That would be very ambitious.
Yeah.
So right now, I'm actually trying to grasp the meaning of all of this, right? So through trying to use one-dimensional systems because they're fairly easy to even compute exactly if you need to, right? But yeah, I mean, there's nothing in this method that prevents it from going to higher dimensions. Could be 2D, 3D, whatever you want. I mean, there is nothing here that really knows about the dimensionality of the system. I mean, at least in terms of training sets and feeding the model. Obviously, you know, once you feed out the information, the neural network is going to figure out, oh, what the hell? They're giving me a lot of data for a 5-dimensional system, right? So it will try to find it out through the correlations. But yeah, but in principle, it doesn't, you know, you can feed whatever you want. So yeah, I don't know. I think I'm not so ambitious yet, George. I think we're still grasping with the basics here, but it could be that maybe one day either this method or a combination of this with something else that people have, you know, thought through and works better. You know, I don't know. There's actually quite a bit of people now using these machine learning techniques. And sometimes what they're good at is, I mean, that's what they're created for is you know, they're good at finding correlations where, you know, you can't see it by naked eye or, you know, or very easily, but they seem to be able to pull them out of the data and then use it very, you know, I wouldn't say intelligently, right? I would say efficiently to make predictions. So I think that's the cool thing about this method. But it's bound to be limited because we know there is no free lunch, right? So eventually, you know, a many body system, you can try to, you know, you can try to beat computational costs at a certain point, but eventually everything is going to have to scale exponentially, right? Because a lot of these problems from, you know, it's interesting, maybe, I don't know how much people know about that, but a lot of these many body quantum problems, they can actually be mapped onto computer science problems, often in the class of optimization problems or satisfiability problems that have been proved to be very tough, right? And for some of these problems, there are no non-efficient algorithms. And in some cases, people are pretty sure that there will never be anything. So if you come up with a solution to a problem that can be mapped onto these more complicated problems that is not scaling exponential, either you're a genius and you're going to get, you know, I mean, a big prize sometime in the future, or you're exaggerating your claims, right? Okay. So. But I don't know. I think, you know, we are making strides. We are evolving. We are finding better ways to do computation. But I'm sure that we're always going to hit, you know, a wall at some point. Unless maybe you can use a quantum computer, you know, to do the simulations, which, you know, maybe that's the way to go.
Okay.
Yeah.
Thank you. I think Sergio wants to ask a question. Hi, Sergio.
Hey.
But we are not, we can't hear you. We can't hear you. Let me see here.
Oh, I see Sergio now. Hello.
Yeah, it indicates
we can see
here.
You, we can't hear you.
Yeah, it indicates here in your icon.
To activate your.
Yeah, in your icon here, it doesn't show either a microphone or a headset. So maybe if you go out and then in again, it will activate your, or maybe if Nancy's there, right? Oh, you guys are not in the same office, okay. Well, the question is one Q is whether, one question, I thought Q was a wave vector. One Q is whether one can extend the approach to a chain with next nearest neighbor interactions. Say.
Yes, yeah, so, well, Sergio disappeared, but I can answer.
I think he went to Nancy's office.
That could be, well be, yes. I don't know if we have to wait for him. Yeah, so, oh, I see an answer coming. Oh, there, both of them. Hey,
window.
guys. So, yeah, so the answer is yes.
Unmute your microphone.
Yeah.
Okay, can he?
Just unmute.
Yeah.
You're still muted.
Yeah, I can't hear you, but I can see your question on the chat. So let me go ahead and answer it.
It's still muted.
Yeah.
Sorry.
Okay.
There you go.
Michael, there. Yeah.
Is it now?
Okay.
We're theorists.
Hello,
we
guys.
don't know how to operate machines.
Hi.
Right. So
Well,
yeah, it's great to see you.
Yeah.
So let me answer your question then. Yeah. So the answer is yes, you can. The trick is just to do the training. So the machine learning part doesn't care whether you have nearest neighbor, next nearest neighbor, or all connected. Obviously, eventually you're going to have to pay the price because it's a very complicated problem. You probably have to train a lot. But the convolution part itself, the CNN, doesn't care about interactions. You're going to have trouble though to prepare
the trick about
the sets.
non-commuting variables. That would work.
Yeah. So yeah, exactly. So if you're going to have some trouble preparing your set because you have to have exact solutions to do the preparation, right? And if you have a very complicated Hamiltonian, may not be easy to just to compute things. On the other level, which you mentioned, which is a good one, yeah. So it might be that you find that you need to keep track of more channels, right? Maybe you keep track of more non-commuting variables. So if you have now a set of 3 non-commuting variables in your problem, maybe you have to keep track of all of them. Yes. And again, that's something that we should be able to check because and as I mentioned, we also had the XXZ model that we did some calculations there. We are redoing those. I don't have the results yet. So there we might be able to see, or even if you do alternating interactions, I have to think about a good way to generate more non-commuting variables. But yeah, we could try to check it out. It's a good point.
Okay. And sort of another question is, so when you can sort of check the accuracy, right, by a direct solution or whatever, that's great. But if you start going, beyond that, how do you know that your neural network is still being accurate enough? And so is there something that you can monitor to tell you when the neural network is doing a good job, other than accuracy with a known solution?
That's right. I don't know, because we're, as you move into larger times, you're really going to, unknown terrain, right? That's exactly what you're trying to predict, because you don't know anything about. It's hard to think, I don't know if there might be, maybe if you have conserved quantities, you can try to check if you still satisfy symmetries or conserved quantities, right? Once that breaks down, okay, if this is making water, probably you're out of of the lane already.
Yeah.
So, but I have to think more carefully because, I mean, it's a good question. And I keep bugging my students with similar questions because I want them to actually push for a comparison also with the exact diagonalization. And they say, well, we can't do anything, after 10 spins. I said, no, you can. You just have to put more effort. You can do bigger systems, right? And so that's one thing we're trying to do. But let's say if you go to 30 sites, that's really hard to do, exactly. I don't think it's doable. You might still be able to do maybe with, DMRG, MPS, but you start to lose accuracy quite rapidly, actually. Yeah.
Okay.
So you don't have a very good comparison base. Yeah.
Right. No, but I like your idea of checking conserved quantities, because those will have to, and then that will be a nice flag. I just had one last question, and that is that I would request Caio to maybe send us a handwritten note so that we can really check that you handwriting.
We can check, yeah.
Thank you.
I think I have a sample here somewhere. I'll try to send you.
Yeah, you're going to be amazed. His handwriting is beautiful. Yeah.
It's impressive, yes.
I'm trying to get known by other qualities than that.
Well, at least you have one. Come on. Yeah.
I believe Kyle has a question because he just showed up. No, you don't? I thought you had. Yeah.
Okay.
So if there are no more questions, I have. Yeah, sure. Go ahead. Go ahead.
Yeah, I was actually it's a comment of Mucciolo. My experience, if you go to a regime, maybe the same Hamiltonian or a slightly different Hamiltonian, for instance, along Sergio's question, when you have next year's neighbor interaction in this Hamiltonian. So if you start in that system, if you start with the initial state, for instance, within a sector of which is kind of highly entangled, so time evolution could be very heavy. So in that sense, I think your machine learning will beat any of these methods easily. So I think it could be a regime in which efficiency of the machine learning will be very important. Perhaps the training set could be
yeah, right.
Need to be
I
larger.
think the training set is critical. Yeah, it's true. Mm-hmm. Now, there is a work that came out, a few months ago that's very interesting. It's from a group in Finland where they actually used machine learning to train the coefficients of the kernel polynomial expansion. Right, instead of trying to do the training for the expectation value, they train an expansion. So it's not a wave function, it's an expansion of some observable in a polynomial, expansion. So, and it's amazingly good. So instead of trying to train with the expectation value and then predict the expectation value behavior, they trained to predict the coefficients of the expansion. And somehow this seems to be pretty robust, maybe even be better than doing the expectation value itself. So I saw the paper Adrian Feiging sent to me a few months ago, and I thought it was really cool. So maybe there are variations of what we're doing, like what these Finnish guys are doing, to actually might be better, may actually have better prediction power. Right? But anyway, so just to mention, but thanks for your comment. I think this also you have a good point. Yeah. It just came to my mind, so I wanted to mention because people seem to be interested in this.
Thank you.
Yeah. Any more questions? Anyone? I have just a comment. I'm being kind of devil's advocate here. I recall that Phil Anderson used to be very dismissive of these sophisticated numerical techniques. He used to say that you may even get the right results, but if you don't know how it was obtained, you didn't learn anything. I don't advocate that because I do computational physics, but I kind of see his point, and this seems to be even more so with machine learning. What's your take on that?
Yeah, I mean, I share some of these concerns, but if your goal is to make a prediction, maybe this is the best way to go. I mean, if you really want to understand something very deeply, maybe machine learning is not the best tool because it hides a lot of things, under the hood, right? So it finds all those correlations for you and applies it, and you can't really see them. But if you're really interested in making predictions or, just the end product, let's put it this way, maybe this is a good way to go. If you do not want to ask too many questions. Okay. Right? Sometimes you don't care, to know what's going on under the hood, right? But I get the point. Yeah, I mean, but as things clearly become more complex, we're tackling more and more complex problems. It might be that at some point we're going to have to give up, or at least give in, and say, okay, we are not going to be able to understand everything, right? Maybe general principles, general concepts, but the details are going to be really hard for us to grasp. So we're going to have to find a better way to collect all those details into something that can provide us with some predictive power. Because if we just trust our own brain and the tools that we can handle, by hand, that's not going to be enough anymore.
Yeah, on that.
If I can add to that, George, I
Sure.
think that in that sense, I think that these methods are kind of a black box, but the advantage that they can give us is to collect a lot of results that could help us to put the puzzle together and understand it. I imagine a little bit like the situation in the early 1900s when people were getting all these experimental results and they had to make sense out of them, and we have quantum mechanics out of it. So I think that without doing the experiments, all these methods somehow may be providing us results that we can help understand. No?
Sure.
Okay.
In that sense, it was funny that at the time, that was a long time ago, and we had a collaboration, Elvius group, with Sandro Sorella's group, doing a quantum Monte Carlo calculation, where a very complicated and sophisticated quantum Monte Carlo calculation that only Sandro could do, and we used Anderson's RVB trial wave function, and the results were very encouraging for the high TCs. And then he wrote a paper saying that he changed his mind. That, oh no, so quantum physics can do some, can give some interesting results. But I am sure that if we had used someone else's trial wave function, he wouldn't be so happy. So it depends on where you want to what you want to get, right?
Yeah.